Alright folks, let's get going here. Okay, there, that's plugged in. This is my little test jig here. Arduino Nano, what a handy little guy that is. Plugged right into a standard proto board and provides both 5 volts and 3.3 power out. And I'd use it to do all kinds of things, bootloader loading and a lot of testing. Right now this is configured for an I2C interface, which is like these two lines here into a memory chip, which I'm going to use as a demonstration here. And let's see. Okay, now let's go to take a look at the chip docs to see what we're looking at. Here's the documentation on the 24LC512 512K bit or 64K byte I2C serial EEPROM. 64 kilobytes was the full memory complement of my original CPM computer, for those of you who still know what CPM actually meant. I like this device because I2C is so much nicer to use than SPI. You only need 2 lines and you can put oodles of chips on it because they have their own internal addresses, and that's why I like this guy here. The only advantage to SPI is its speed, but nothing I do requires that much. Looking through the docs here, it's all the usual I2C timing and such. You always have a, where's there, start. Yes, you always have a start and then a, I guess they're not showing it there. There it is. We always have a start followed by the control byte with the address of the chip. This one can have 8 different ones, and then a 0 for write or a 1 for read in the last position. The other device will pull the line low on a 9th clock if it's responding. So this one has a 2-byte address followed by data. It can be multiple data bytes for either read or write. See, read address. Oh yes, the typical read is a start bit, the address with the 0 for write the address, and then another start bit without any stops in between, and then the address with the bit set for read, and then after that you can read actually any number of data bytes. And the only thing you have to remember is the last one you read, you do not give an ACK. Since the external device is talking to you, you are now responsible for ACKing. So for multiple ones here, ACK, and no ACK, and always a stop condition. So now let's take a look at the program and see how that looks accessing this. Okay, we've launched the monitor program by hitting that button on the other screen, and it signs on and gives you a prompt for I2C. I have it defaulting to that. If you well, let's use uppercase because they're easier to see. Commands can be in upper or lowercase. The M switches and you'll get the prompt for SPI then. You know which one you're in. The really cool trick this does is the scan, which is the S command. Now watch this. Okay, it went through all the possible addresses and found A0 is our write address and A1 is our read address. Now, here's how you construct commands to go in there. Everything starts with a slash, which creates the start condition. Otherwise, it'll ignore everything. Our address for writing is A0, and then it needs 2 bytes worth of address. Now, that would write something, but that's no fun unless you can read it back. and that involves doing another start condition. Notice there's no stop in between, just start this, start, and now we do A1, the read address, and what I've done in this program is dot is my read command. It just is a handy, easy to hit with my finger there. And let's say we did 40, and that means we want to read back 40 bytes. Well, let's see how it works. Wow, look at there. There's the first 40 bytes in the chip. As you can see, we've already been in there diddling around loading test bytes. But just to show you how that works, let's load in some more. Always do the start or it will do nothing at all. A0 is the write address. Let's load it in location just for fun. Location 10 hex. Okay. And now since this is a write command, we can just start doing it. How about 99887766? We ought to be able to recognize that. Okay, and here's it shows you that as it sent each one, the exclamation point means it got an ACK. It got acknowledged back from the memory chip, which is a good sign that that chip's really alive. So now let's do this. Let's go back to location 0 by doing this, and 4 bytes is 0. Is that 4? No, that's 4. That's 2 bytes, 4 characters. Okay, now switch it to read mode with that command, and let's dump out 40 from there. And here we are. And this is like 20 per row, just so it doesn't run off the screen here. And there, at the location we specified, is the data we wrote in. So that's basically how it works. Now, of course, this is a fairly simple chip. The idea of this program, especially for more complex chips, is you can work out all of the access to whatever internal registers, try it out. Because here's the thing, folks. No matter how complex the chip is, it's bytes in and bytes out, okay? And I think I'm inserting a graphic here just to emphasize that. And that's what this program does. So hope you enjoy it. Documentation is all on Github. The usual link will be below the video. Y'all have a nice day.